Section 2.3, functions. So the beginning of this section is just going to be a big definition dump. And a lot of it is stuff that you've seen before from college algebra, but now we have all these new tools, right? We've been talking about sets, and so we're going to go back and redefine and give the actual uh, definitions for some of these things. So let A and B be non-empty sets. A function f from A to B is denoted as follows on your screen there. Assigns each element A to exactly one element of B. So this f of A equal B thing that you've been seeing all along really means that f is assigning the element A to B. So it's called mapping. So functions are called mappings or transformations. So we can say that the function f is a mapping or maps A to B. A is the domain of f. B is the codomain of f. And I know what you're thinking already. Why is it not called the range? We're going to get there. You'll see the difference. If f of A equal B, then B is called the image of A under f, and A is the pre-image of B. The range of f, and here we get some new notation, f of set A. So the range is all the things you can map to. You've seen before whenever you've been drawing a function, right? You know, if it's your traditional Cartesian grid function, technically the codomain would be all real numbers, but the function, the range of the function doesn't reach all of those numbers. If S is a subset of A, then f of S is all the things that those elements S will be mapped to in B. So I suggest you kind of keep these close by and look at them. As we're going to see moving forward, it's a saying I like to use quite a bit, but these definitions are all very simple. That's not the same thing as them being easy, and it's not the same thing as them not having a lot of depth to them. Two functions f and g are equal when they have the same domain, the same codomain, and for all the elements in the domain, the mapping f will send it to the same element in the codomain that g would. F is one-to-one or injective if and only if f of A equals f of B. So always keep in mind that f of A and f of B are elements in the codomain. They're in set B. So this would imply that A must equal B for all the A and B in the domain of f. A function is onto or surjective if and only if every element in B can be mapped to. F is if it is both one-to-one and onto or injective and surjective, then it can be said that it's a one-to-one correspondence or a bijection. If we have a bijection, we can then define the inverse of F, and it's the mapping that goes in the reverse direction. And finally, we get a statement here about compositions. If f is a function that goes from set B to set C, and g is a function that goes from A to B, the composition of f with g, right, this is your FOG or your Goff statements, is the mapping that will go all the way from A to C, right? It passes that intermediate step B, but it just follows the mapping all the way through. And so what I'd like to do next, I don't know how often this advice is ever taken, but pause the video, think about these definitions, right? I'm going to post an announcement saying, hey, try to look at these before we go on to the next step, because I'm going to go over some examples applying these definitions. And it's not because these definitions are incredibly important. They're important, but not like the most important thing we do in the course. But I think it's just to give you a feel for the specificity for which these things are written, right? That applying them, even though you read them, you're like, oh, yeah, I got it. Actually using them is a little bit different. So let's define a function f. It's going to go from my set A to my set B. Now in this case, I've decided to take numbers out of the situation, so we can just look at it in terms of elements. And so my set A is shapes, my set B is colors. So every day when you come into my toy factory or whatever, there's a new instruction sheet. So today you showed up and I said, hey, we're doing Operation F. And so you come in, you're going to paint the shapes. And this is what F tells you to do. Circle to red, square to orange, triangle to orange. And so let's run through what this is and what this isn't. So here's the definition for injectivity. F of A should equal F of B. That would, I'm sorry, if F of A is equal to F of B, that would imply that A is equal to B. Do you think that this function meets the criteria to be injective? No, it doesn't. F of square and F of triangle are both colors. They're both orange, but square and triangle are not the same element. So I have injectivity is asking the question, do you map to the same element? So not injective. Is it surjective? No. There's an element, there's a color here that's not used. Blue. Blue is in the codomain, but the range does not get to it. There is no shape that's mapped to blue. So in conclusion for this one, not injective, not surjective, so it's not a bijection, so there's no inverse. You come in the next day, and now you're asked to do G. Right, same, essentially the same function as F, only we're out of blue paint. It's just nowhere to be seen. Is it injective? No, for the same reason, right? We have square and triangle both mapping to orange. Is it surjective? Yeah, every element in B gets mapped to. So it's not injective, but it is surjective. It's got to be both to be a bijection, so it's not a bijection. And as it's not a bijection, there is no inverse. Let's try H. Is this injective? Sure. Every single time I map to a color, there's only one shape that maps to that color. Is it surjective? Nope. There's the color green, but there is no shape that maps to that color. So here we get a function that is injective, but not surjective. It's not a bijection because it's not surjective, and so there's no inverse. Let's take a look at R. Is it injective? Yeah. Everything gets mapped to by exactly one element. Is it surjective? Yes. For every element in the codomain in B, there's an element that maps to it. So it's injective, it's surjective, so there's a bijection, and so the inverse does exist. If you go back and look at all those other examples, there are cases where I could have given you a shape, given you a color and asked, what shape is this? And you would know, right? Because in the traditional sense, you come into work and you would say, okay, I have a circle, what color does it need to be? But for the inverse to exist, I would need to be able to say, I'm holding a orange shape, what shape is it? And this is the only one where you can fully go back. You can hit the undo button. And because of this, you can almost say that the two are interchangeable, right? It doesn't matter if you told me circle or red. You're talking about the same object because a red object is a circle and a circle is a red object. So in this sense, we get what's called a bijection. Let's check one more example. Here's the function t. Is it injective? Is it surjective? Is it a bijection? None of them. It's not a function. So it's violating two parts of this. First of all, not every element in A is assigned to anything, right? Triangle is not assigned to anything. To make matters worse, if you're holding a square, you don't know what to do with it. Do you need to make it orange or do you need to make it blue? So this is not a function. We have a couple specialty functions we want to talk about versus the floor function. And the floor function is the largest integer that is less than or equal to x. And I just encourage you to think about this one for the second because it sounds weird that we're saying the largest that is less than. This essentially works out to be always round down. So the floor of a half, 0, right? We're kind of just cutting off the decimals. Floor of 1, no decimals to get rid of, it's a 1. 2.9, round down, 2. These are all pretty straightforward. Where this gets tricky is with the negative numbers. The floor of negative a half is -1 because negative a half is greater than -1, but we need the largest integer that is less than, right? What are the integers less than negative a half? -1, -2, -3, and we need the largest of those. Whereas the floor of -3 is still just -3. This is sometimes called the step function as well. And this is what it looks like, right? For anything between 0, including 0 to 1, you will round down to 0. Similarly, we have the ceiling function. This is where the smallest integer that is less than or equal to x. This is always round up to the closest integer. The function looks very similar to another stutter step, but do note that it occurs in a slightly different place here. And one that's going to be really, really important to us, the factorial function. So this maps the natural numbers to the positive integers. So it's denoted f of n as n factorial. So n factorial is equal to, you multiply everything from 1 through n. So 1 factorial is 1, 2 factorial is 2, 3 factorial is 6, and 4 factorial is 24. This one, again, is going to show up quite a bit later on in the course. It's going to be pretty important.